Hi there, my name is Weibo Wang. I am with TELUS Corporation. In case this is the first time you hear about TELUS, we are one of the largest telecommunication companies in Canada. As many telco companies, we have been extensively using SaaS in our daily operations for many years. It is a great pleasure for me to be here today, also representing Gary and Libo, my team members here in TELUS, to meet with everyone and share some of our experience with SaaS in our work. Presumably, many of us have been working on data for years, and we have seen how this industry has been evolving. I still could remember those old days when I just got started. Most of my daily work was just various kinds of data manipulations, and perhaps with some statistical analysis, all kinds of statistics and p-values. SaaS undoubtedly has the most comprehensive and trustworthy tools for all this data work. Gradually, our works have been shifted more and more to statistical modeling and machine learning, where again, SaaS has been a great help with all its excellent regression procedures and descent tree procedures. We all know how complicated the data itself and the machine learning targets can be nowadays, which is a challenge to data scientists. How could we use all the analysis and the modeling procedures in better ways to fully unleash their power in order to finally come up with great applications? Today, we are about to show you some of our experiences on building bagging trees by SaaS programming and comparing our approach with other options.
I will start with a few words on bagging. Bagging is the short term for bootstrap aggregating. It is a well-studied ensemble learning strategy to improve the stability and accuracy of relatively simple modeling methods by reducing variance and thus reducing the risk of overfitting. Bagging generates n new training sets. By sampling from the original training set uniformly and with replacement. By sampling with replacement, some observations may be repeated in each new training set.
If you have SaaS VIA, you can use proc forest procedure, doing bagging uncomplicatedly with the in-bag fraction option. Or, if you have SaaS Enterprise Miner, the HP forest procedure can build a random forest with bagging your data. What we will show you today is one more solution for implementation with relatively lower cost. We just used a descent tree to illustrate why this idea would be valuable. Descent tree method has been a popular analytic approach for decades, thanks to its intuitive approach, interpretability, and flexibility with input data. However, tree methods are prone to overfitting and unstable performance due to various common issues. These minor disadvantages call for strategy for improvement, especially in the practical machine learning pipeline. Ensemble strategy is arguably the most favorite choice in the last 10 years, thanks to the rapid development of computational power. It is pretty simple to bag your data in SaaS. The survey select procedure has the URS, which is unrestricted random sampling option for us to do so. The unrestricted method can help you to select records with replacement. This macro you are seeing on the screen is able to create n new training datasets from the original training data with replacement. Let's talk about a descent tree, a single tree. Presumably, we are all familiar with decision tree. A high-level summary would probably be, a decision tree is a very popular and powerful tool for supervised learning. It can be used for making both classification and regression type of learning and prediction. This method has been well studied for decades, and there are lots of smart ideas and tricks that make it versatile. Decision tree is available in SAS by Proc HP Split, which, simply put, is a truly brilliant procedure. The HP Split procedure is a high-performance procedure that builds tree-based statistical models for classification and regression. The predictor variables for tree models can be continuous or categorical. If we have categorical predictors, we can simply specify them as class. You probably could imagine how much effort could be saved simply by this option. There are many slightly different strategies criteria when talking about how to grow a tree, such as Gini index, entropy, or residual sum of squares. We can specify your option in grow. We can also define how deep we want to grow our tree and where to stop by making specification in rules. Once the rules are set, the process of building a decision tree begins with growing a large full tree. However, one of the concerns of growing a full tree is that a full tree tends to overfit. To reduce that risk, one trick is to prune the tree with some standard, such as cost complexity pruning. This functionality is supported here by prune. With these options, we could build a decent tree model in a relatively short period of time. One of the main reasons why people love decision tree is its transparency and interpretability. With procedure HP Split, SAS provides great visualization of the structure of the tree, so that the data scientists can present the model to their audience, like what are the main drivers, what are the key data points, etc. Once all parties are aligned on the final model, procedure HP Split will output the entire tree structure as a series of if-then statements, which is very generous and sweet. One last feature I'd like to mention is that Proc HP Split runs in either single machine mode or distributed mode. Okay, we just talked a lot of great features about Proc HP Split. But the data that we're dealing with in real world can be really challenging. Sometimes the score from a single tree is not smooth enough. Sometimes the performance of a single tree just can't be stabilized. This is why we need a strategy called bagging. To better understand the potential of the HP Split procedure, we tested a few similar but different approaches based on decision trees and compared their performance based on the bank marketing data available from the UCI machine learning repository. The data has 41,000 records for direct marketing campaigns of a Portuguese banking institution. More than one phone call to the same customer was required in order to assess if the bank term deposit would be or not be subscribed. 70% of the data were randomly selected as training data, and the other 30% will be used to validate the result of each algorithm. For comparison, we built two decision trees using the HP Split procedure with and without pruning the tree respectively, and built another two trees using Python scikit-learn package with pruning and without pruning as well. All four trees have the same max depth, max branch, and the same other settings, This is the ROC and EUC from the 4 trees applied to the 30% validation data. We can see that the results from both tools are very close. The main difference came from whether or not the pruning strategy was applied, rather than which tool is used. Next, we will compare our bagging tree method with random forest from the Python scikit-learn package. To build bagging trees, firstly, we create n new datasets from the original training data. Then, use the n new datasets to build decision trees in parallel. The final result will be based on the majority voting or the average prediction value from all the trees. We already know that service select procedure can bag the data. We also know that HP split procedure can build decision trees. I have a bagging, I have a tree. Ta-da! Bagging tree. By appending the HP split procedure after the service select procedure in the macro which was shown earlier in this presentation, we can build bagging trees in SAS. A new parameter target was also added to reflect the response variable that would be predicted in the model. The n new datasets generated by service select procedure were used as training data to build n trees. This chart compares the performances of bagging trees and the random forest built with Python scikit-learn package. Random forest is one of the most popular algorithms in machine learning and predictive modeling due to its great performance. It is a tree-based ensemble algorithm, which builds a number of single trees from several to hundreds. Outputs from these trees are aggregated as the final results. To maximize the predictive power, minimizing similarities among trees is required. For example, trees need to be as independent as possible from each other. The higher variances among trees mean better prediction. To help building distinct trees, bagging is used in random forest too. The fundamental difference between bagging and the random forest is that in random forests, only a subset of features are selected at random out of the total, and the best split feature from the subset is used to split each node in a tree, unlike in bagging, where all features are considered for splitting a node. First of all, let's look at the performance of a single tree with a pruning strategy applied. This is perhaps the simplest tree model that anyone could easily try, and having pretty decent performance almost immediately. If we wanted to push for better performance by building a low bias tree and averaging out the variance with bagging, we can see the strategy would work with a small number of bootstrap samples, like 5. And when we increase the bootstrap samples to a moderate number, like 20 or 50, the performance of our algorithm can be significantly improved from a single tree. The rest methods are various random forest, in similar fashion as our bagging trees. As we can see, the performances are also very close in various scenarios. Therefore, we have confidence that our bagging strategy can help you achieve best-in-class predictive performance in the computing environment that you are familiar with and with almost no extra cost. We'd also like to take some time to share some experiences about how we implement this method in real work. First is to create a folder to keep all the SAS data step files generated by the code statement from each tree. And to use them to score other data is pretty simple. just use an include statement, the probability scores will be in the output data. We include the validation data into the macro when build the trees. All the scoring data will be appended into the dataset valid, which we can use later to calculate the average probabilities of all trees for regression, or to vote the majority prediction of each tree for classification. We also output the feature importance details and append the details from each tree into the dataset var_IMP here, which is variance importance. We can calculate the average importance from all the trees to do feature selection or to explain the model if necessary. Here's the example of how we use the dataset valid and var_IMP to calculate the average variable importance and average probabilities. We can see it is pretty straightforward. Only a few lines, we can get the results from bagging. Now we see that this method has a lot of advantages. It does not request extra cost. It has great performance, not only predictive performance, but also the ability of dealing with really large data. It is also easy to be implemented in real work, but still, it has a disadvantage. Let's see, if we have 1 million records, 1,000 variables to build 500 trees, it could take a while for a single call to complete the very first iteration. We could use multiple calls and leverage parallel computing to speed things up, which is one of the fundamental advantages of bagging. For this, we highly recommend SAS Viya, which will take care of computational resources for you. We could also use various variable selection approaches in order to come up with a better model for practical implementations. For this scenario, what we usually do is to compare algorithms built on different numbers of trees and different numbers of features to find out the optimal cutoff. For example, at the beginning, we use all the features to build several algorithms with different numbers of trees. Then use the 200 top common features from the previous models and repeat the development again. Then perhaps select the top 50 features from the previous step and then iterate again until any reduction of performance is observed. Among the algorithms with equivalent performance, we would prefer the one with simpler structure and features for model interpretation and easy maintenance going forward. Lastly, I'd like to express our appreciation for giving us this great opportunity to present our idea here. Hope everyone stays safe and healthy, and have a great day.